Let's continue looking at more properties of our logarithmic functions. So there's two special bases for logarithmic functions. So when it comes to our bases, any number as long as it's larger than 0 and it's not 1 can work, but there's two special ones that we use the most. So log base 10, because we're in a base 10 number system, everything is usually done base 10 that you're used to seeing. We're just going to write that as log, right? There's no base listed. It's just log. So if there's no base, immediately think that that base is really 10. So if there's no base listed, it's just a base 10. Now, instead, the other one is going to be log base e, because e we saw appear in our exponential functions. E was this random constant that was 2.7, 1828, 1828, 4590, those types of things. So log base e, that e tells us that if that's the base, we actually write ln. So this is ln, and then whatever we want. So this is called the natural log. We're going to be using this natural log all the time moving forward. This is going to be probably the most popular logarithm that we're going to use in this class. So it just happens to be log base e. So there's a little e down here, but we don't write it. Then let's take a look at some examples that use this. So if we want to solve this equation, so again, if we're trying to solve something about logs, we want to use exponents instead. It's easier to think about that. So what I have here is I have to convert this to exponential form. So if we think about this, I have the base raised to this exponent is this number. Because there's no base listed, that's really base 10. So this becomes 10 to the 0.0124 is equal to x. And now just plug this into your calculator, and you should get something like 1.029 is equal to x. Now you could check your answer. Your calculator, most normal calculators, will have the ability of doing log base 10 and natural log. You use your calculator and you try to say log of 1.029, plug that in, you'll get pretty close to 0.0124. It won't be exact because this is rounded, but at least it'll be close. Here, if we look at natural log of x equals 6, we're trying to figure out what is this x. Again, convert this to exponential form. But remember, this natural log that says that the base is e. So I have e raised to the 6 is equal to x. So this would be my exact answer, right? There's no rounding taking place here. Just like how technically this would be an exact answer, there's no rounding. But often if you just want to be able to get a regular decimal number, e to the 6 is going to be roughly 403.9 or 403.43. So that is roughly e to the 6. And again, put that into your calculator, practice the calculator tools to see if you can get this. So one other thing I want to take a look at now, again, is looking at this relationship between exponents and logs with them being inverses. So since f of x equals b to the x and this other function, g of x, is log base b of x, these are inverses of one another. As long as the bases are the same, they're inverses. What happens when you look at their composition? So for composition of functions, you're putting one function inside the other function. So if you try to recall what we had was we had this inverses of each other. The composition we had was say f of f inverse of x would equal x. So as long as these are inverses, and the same thing was true if we switch the order. F inverses of f of x is equal to x. So whatever was on the inside, that just basically appears. You're able to cancel everything else. So in this case, what this says is that if these are inverses, I have b, if I put in log base b of x wherever the x is, I have b raised to the log base b of x. This is equal to x. So whatever number's there, that becomes the answer. Similarly, if I now do the composition the other way, if in this function I put in b of x everywhere there's an x, if I have log base b of b raised to the x, that is also equal to x. So if we see, what does this mean now if I look at examples? Natural log of e to the negative 0.52. The base of natural log is e. this is also e to some exponent. So this is going to be very much like this. My base is e, this base here is e. They're the same, so the only thing that's left after this cancels is negative 0.52. So that's my answer, negative 0.52. Same thing now, 10 raised to the log of 100. Remember, log without a base written is log base 10. So if I have log base 10, but the base down here is 10, these match. So the only thing I'm left with is the answer on the inside, which is 100. Now this one, log base b of 1. So for any base, what is this equal to? Now this gets tricky because now the base on the inside, we maybe like to use this, but 1 doesn't really have a base that's b. But we do know that this could be written as log base b of b to the 0. Right? Any number raised to the 0 that we're allowed to plug in here will be equal to 1. So now using this property, this ends up being equal to 0. So log base b of 1 is equal to 0. This is log base b of 1 is equal to 0. This is going to be a huge one that we're going to use very, very often. Log base b of 1 is equal to 0. The other one that's also similar is log base b of b. So log base b of b is not going to be 0. The exponent here is 1. So this is going to be 1. So we're going to use both of these quite a bit to be able to simplify different expressions as we continue to progress through this chapter.